So let's finally calculate our first double integral. So this is problem 1. Calculate the following double integral on area A of this function x times y squared plus x with respect to the area A. And I'm telling you that A is bounded by x between 0 and 1 and y between 0 and 1. So this is a rectangular area, okay? So we are being asked to calculate this double integration. So first remember, what does this double integration mean? So we have our x and y planes. So this is x, this is y, and this is our function x, which is a function of x and y, right? So this is our function of x and y that we are integrating. This is the integrand. So we are integrating between x goes from 0 to 1, and y goes from 0 to 1. So we are integrating in this area here. This is the area of integration. Okay, and what are we integrating? So we are integrating this function f of xy, which will be some surface in 3 dimensions, right? Defined in xy. So I'm going to pretend, although the shape of the actual function would be very difficult for me to draw, I'm going to pretend it has a different shape. Okay, so let me draw some arbitrary shape that looks something like this. So let's pretend this is our function f of xy. So by asking you to calculate the double integral of f of xy in this area A, I'm asking you to calculate the volume of this block, which is the block between the surface and the xy plane. Okay? Notice that if the surface crossed the xy plane and it became negative, then I would be subtracting the volume that is below the xy plane. So it's the positive volume minus the negative volume. Okay? Similarly to how one-dimensional integrals worked. So let's do it. We know that this volume will be double integral on A of f of xy with respect to A. So let's start. Volume is equal to the double integral on A of my function dA. So I'm going to apply Fubini's theorem, okay? And what did Fubini's theorem say? That I can do an integral inside of an integral. So let me first write the parentheses. I write the function here. And now I have to choose an order of integration. So let's do first I do dx. So that will be the inner integral, and then I do dy. So the outer integral will be along y. So now I have to write the limits. What are the limits? So first let's look at the inner integral. So this integral is with respect to x, so the limits correspond to the values of x, which goes from 0 to 1. So we write 0, 1. And the outer integral is with respect to y, and this will correspond to the limits also 0 to 1, because our rectangular region is very simple. So now we have to do these two integrals. So it's one inside of the other, which means first we have to do the one that is inside, okay? So let's keep the integration symbol outside for dy, and now let's do the integral of this with respect to x. So in order to not get messy, let me write the integral of this here in a bracket here. So we are doing the integral between 0 and 1 of, let me expand the brackets, so this is xy squared plus x squared dx. So I have to do the integral of that. So I have to find an antiderivative. So what function, when I calculate the derivative, gives me this? So that is very easy. That should be 1/2 x squared y squared plus 1/3 x cubed. And this has to be evaluated between x equals 0 and x equals 1. Okay? Notice that when doing this integral, I have treated y as if it's a constant. So imagine that y here was a pi or any other constant, yeah? So it didn't affect my integration along x. So now I have to evaluate this at x equals 1 and x equals 0, which is very easy. This is just 1/2 times 1 squared, so 1/2 y squared plus a third. Okay, and that is my result for the inner integral. Okay, so now I write that here. And notice that this is now a function of y only. The x has disappeared because we have substituted the limits when we did the integral along x. So there is no x anymore. And this is very good sign, because now it means that we can do this integral with respect to y. So we can calculate this integral, and we need to find an antiderivative of a half y squared. So what is that? It's 1/6 of y cubed, such that when I calculate the derivative, I get a half y squared plus 1/3 times y. And this I have to evaluate between y equals 0 and y equals 1. So the result is simply 1/6 plus 1/3, which is equal to 1/2. So now the dependence on y disappeared because we substituted y. So now the final answer, which is our volume, is a constant that doesn't depend on x and it doesn't depend on y. So we have calculated our first double integral. Excellent. You can see that actually it's relatively easy. We could have done it the other way around, and I encourage you to try it out. So first integrate along y, so put dy here, and then the result will be a function of x that you can then integrate along x outside. So I encourage you to try that out. Thank you very much. See you in the next example.